Have you ever taken a deep breath of air and wondered, what exactly are you breathing in? I mean, it's completely invisible to the naked eye, right? It doesn't seem to weigh anything in your day-to-day life, and it just kind of floats around us. It's incredibly common to think that because we can't see gases, they must not really be made of anything substantial. So is an invisible gas actually made of matter? Well, it's a huge misconception that gases aren't matter just because most of them happen to be completely out of sight.
Welcome to This Explainer. Today, we're going to completely shift the way you look at the everyday objects around you. We're peeling back the invisible layers of reality to reveal this hidden microscopic world of atoms, molecules, and energy that dictates absolutely everything we see, touch, and breathe. By the end of this, you won't just see a glass of water or a wooden desk. You're going to understand the bustling, energetic metropolis happening right inside of them.
Okay, let's dive into this. Here is our roadmap for today. First up, we'll meet the matter. Second, we'll expose the secret life of solids. Third, we'll check out liquids on the move. Fourth, we'll explore the invisible world of gases. And finally, we'll wrap up with changing states.
All right, kicking things off with Section 1. Meet the matter, the building blocks of literally everything.
So before we can talk about how states of matter differ, we really need to understand exactly what is doing the moving and the changing here. It all starts with the atom. An atom is defined as the smallest unit of an element that actually maintains the properties of that element. Think of atoms as the absolute foundational building blocks of the physical universe. Whether it's the screen you're looking at right now, the chair you're sitting on, or the star at the center of our solar system, matter exists in all these different physical forms, but at the end of the day, it is fundamentally made of atoms.
But here's the thing. Atoms rarely like to fly solo. They attract other atoms and combine to form what we call molecules. A molecule is just a group of atoms that are held together by chemical forces, and it represents the smallest unit of a compound that keeps all the properties of that compound. And here is the absolute secret to everything we're talking about today. These particles inside a substance, they are constantly in motion. They are never, ever truly still.
Now, the real game changer behind all of this motion is kinetic energy. As defined here, kinetic energy is simply the energy of an object that's due to its motion. This is the crucial driver. It's the speed of these particles, their kinetic energy, combined with the attraction between them that strictly dictates whether a substance takes the physical form of a solid, a liquid, or a gas.
Which brings us right into Section 2, the secret life of solids, moving while standing still.
We're going to dismantle a very intuitive myth right now about the macroscopic objects you interact with every single day. I want you to literally reach out and tap your desk, or your phone, or whatever solid object is closest to you. It feels entirely stationary, right? Super rigid. Well, a massive misconception in science is that the particles making up solid objects don't move at all, that they have absolutely zero kinetic energy. So let me ask you, do the particles making up your solid desk actually move?
The answer is yes, they absolutely do. Each atom's electrons are constantly zipping around in motion, and furthermore, even the atoms themselves inside those solid structures possess a small vibration. Even though they're fixed in their overall position and packed tightly together, they are practically buzzing in place. They don't move much in terms of actual distance, which means they have very low kinetic energy, but they are absolutely never frozen still.
To really visualize this, let's use an analogy. In solids, molecules are packed together in a definite arrangement and are strongly attracted to one another, which leaves almost zero room for them to move. Think of it like being in a ridiculously packed crowd at a concert. You're stuck in your spot, right? You can sway, you can vibrate, you can maybe wiggle your arms a little bit, but there's no way you're walking across the room. Because the molecules only have room to vibrate like this, solids maintain a fixed, definite shape. Let's turn up the kinetic energy and move on to Section 3, liquids on the move, sliding through space.
As we shift our focus to liquids, we see how the microscopic structure fundamentally changes how matter behaves. Now, because liquids can be poured so easily, another big misconception pops up. People often assume that the particles in a liquid simply don't hold together at all, just because the liquid is fluid. They picture these liquid particles just freely floating away from one another like tiny disconnected islands. But is that actually the case?
Looking back at our crowd analogy, we can see exactly why that's false. Forces between particles in a liquid actually hold the molecules much closer together than you might think. Definitely way closer than in a gas. This is what makes liquids quite dense. However, the attractive forces just aren't quite strong enough to keep the molecules completely locked down in a fixed position. So, returning to our analogy, a liquid is more like being at a mingling party. You're confined to the room itself, sure, but you are completely free to walk around and slide past other people within that defined space. Because the molecules can slide right over each other like this, liquids can be poured and naturally take the exact shape of their containers.
All right, now let's break free entirely in Section 4, the invisible world of gases. Free to expand.
This circles us right back to that very first question we asked at the top of the explainer. Even though we can't see them, gases have very specific, measurable properties that completely prove they are matter. First off, they are comprised of widely separated molecules. Unlike our solids or liquids, there's practically no significant attractive force between the molecules in a gas. And because of this lack of attraction, a gas will rapidly expand to completely fill whatever container it finds itself in. Just think about breathing. When you pull air into your lungs, that gas expands to fill them up entirely. Now, because the distance between the molecules is so vastly large, gases have an incredibly low density. And a really unique feature of all this microscopic empty space is that gases can actually be compressed and stored under pressure. It's exactly how those cans of compressed air work when you're blowing dust out of your computer keyboard.
To put a bow on our crowd analogy here, if a solid is a mosh pit and a liquid is a mingling party, a gas is basically like being outside in a massive, wide-open field with a group of people who are just running around, completely free to move rapidly in any direction they want. They're far apart, they're moving fast, and they're filling all the available space.
And this brilliantly illustrates everything we've talked about so far. This matrix elegantly brings all the pieces together. Look at how the differences really just boil down to motion and attraction. You got your solids with tight packing, fixed shape, totally uncompressible, and very low kinetic energy. Just those tiny vibrations. Then liquids are packed a bit looser, they adapt their shape to the container, they're mostly incompressible, and they have that medium kinetic energy that lets them slide. Finally, gases are widely separated, they completely take the shape of their container, they're highly compressible, and they possess super high kinetic energy.
Which leads us perfectly into our final segment, Section 5, Changing States, Energy Shifts. You see, matter isn't stuck forever in just one state. By manipulating kinetic energy, we can actually force a substance to transform. Heating and cooling directly change the kinetic energy of the particles. Let's look at melting. Step 1. You add heat to a solid bar of chocolate. Step 2. That thermal energy transfers right into the chocolate, causing the kinetic energy of those tightly packed particles to spike. They start vibrating faster and faster, and eventually, that vibration overcomes the strong attractive forces holding them in that rigid structure. Step 3. The molecules literally break from their fixed arrangement and begin sliding past one another. Boom. Your chocolate has successfully turned into a liquid.
Now the exact opposite is true for cooling. Step 1. Take a liquid, maybe some fruit juice, and cool it down by tossing it in the freezer. Step 2. As the heat is removed, the kinetic energy of the liquid's sliding particles starts to decrease. They really begin to slow down. Step 3. Because they're moving so much slower now, the natural attractive forces between the molecules take over again, grabbing hold of the particles and locking them right back into a fixed, definite arrangement. The juice changes state and becomes a solid popsicle.
But wait, heat isn't the only tool we have at our disposal. We also have pressure. Because gases have so much open space between their rapidly moving molecules, pressure has a massive effect on them. Increasing the pressure on a gas physically forces those widely separated molecules closer and closer together, compressing them into a much smaller volume. In fact, if you cool a gas down to slow the particles and apply enough pressure to force them close together, you can actually change that gas straight into a liquid.
So we've journeyed all the way from the tightly packed, buzzing world of solids, through the sliding, fluid dynamics of liquids, straight into the rapid, expanding freedom of gases. It all comes down to atoms, molecules, and kinetic energy. I want to leave you with this one thought. Look around your room right now. Based on what you've learned today, how many different states of matter can you spot? And in your mind's eye, how fast do you think their microscopic molecules are vibrating right this very second? Keep exploring, and thanks for joining me on this explainer.